Tonight we're going to go over section 3.2, measures of spread. Y'all remember Monday night we talked about measures of center, correct? What were the measures of center? Mean, median, and mode. I'm going to put a table up here and see if y'all remember when I talked about this. Remember when we introduced the concept of population parameters and sample statistics, and I said there are certain variables that we use strictly with populations and certain ones that we use strictly with samples. And they measure the same thing. Last Monday night we talked about measures of center, and one of them was the mean. Do you remember what the population parameter was for the mean? Mu. The population parameter is mu, and you make it like that. What was the sample statistic we used for the mean? X bar. It's an X with a bar over it. Another measure that we're going to learn tonight is called the standard deviation. And I'm going to go ahead and tell you right now what that symbol is for the population and what it is for the sample. The standard deviation population parameter is a lowercase sigma, and you make it just like you saw me make that right there. For the sample statistic, then, we use a lowercase s. The first measure of spread that we're going to look at tonight is called the variance. The variance is just the square of the standard deviation. So if you know one, it's easy to figure out what the other one is. So this would be a lowercase sigma, and this would be a sigma squared. This was s and s squared. Another measure we talked about was a proportion. It'll be a while before we look at population and sample proportions, but I'm going to go ahead and put them on this table. This table is something that you probably want to put on your formula sheet so that you have it, or on a note card even, so that you have it handy whenever you're doing work. We use a lowercase p for the population proportion, and we use a p hat for the sample statistic. We just put this little rooftop shape over the p, and we call that p hat. Another measure that I mentioned before was the size of something. The population size, we use the variable n, where it's an uppercase N for the population, and we use a lowercase n for the sample. All of these parameters are associated with the population data. All of these parameters are associated with sample data. And tonight we're going to be looking at how we calculate the standard deviation and the variance for both the population and for the sample. This symbol right here is pronounced mu. In green I'll put the pronunciation for the symbols. This is mu, sigma. This one right here is sigma squared. P and N, I'm pretty sure you know what those are, so I'm not going to write those down. This is pronounced X bar, and this one's pronounced P hat. A major challenge with learning statistics is learning the terminology. And unless your brain just thinks in symbols, sometimes it helps to have words associated with the symbols. And green are the words that you would be thinking in your mind, or if you were discussing statistics with somebody, you would say the words that I have written out in green. They correspond to the symbols that we see here. A lot of the first part of this course is just getting the terminology and the language down. So starting back at the top, section 3.2 is measures of spread. Here are the objectives that we're going to go over tonight. I'm going to mention these two, but they're not in the homework. It wouldn't take that much to explain them, and plus I don't know where you're going after this course. You may want this information for something that you'll be doing in the future. And these two relate to number 5. Objective 1 is computing the range of a data set. When I talked about the center of the data, especially if I had a normal distribution, do you remember this shape is called a normal distribution? Your book doesn't refer to it as a normal distribution until about chapter 6. It refers to it as bell-shaped or symmetric and unimodal. This is a normal shape, and with a normal distribution, the mean would be this number that's right smack dab in the middle. That would be X bar if I was talking about a sample mean. When I'm referencing the spread, I'm just talking about how spread out these data values are, how far out they go. The range is a measure of spread that's very easy to calculate. We just look for the lowest data value and the highest data value, and then we subtract those two numbers, and then the result would be the range. It's very straightforward and easy to find. We don't do a whole lot with the range other than use it maybe as a descriptive statistic if we're reporting information about data, because it's very sensitive to outliers. One outlier, an extremely large or an extremely small value, will greatly affect the range. Objective 2 is to compute the variance of a population and a sample. Well, the variance is the square of the standard deviation. And this book, they present the variance first, then the standard deviation. But I want to give you a little explanation about what a standard deviation is before I talk about the variance. This part you don't have to write down, just sit back and listen. It'll help you understand what a variance is if you can understand what a standard deviation is. The first measure of center that we looked at Monday night was the mean. How did we find the mean, an average? We add up all of our x's and then we divide by how many x's we had. A standard deviation is a numerical value that we can think of as being an average deviation. So for example, let's say that I have some data values, and I'm just going to use a two-dimensional plot for this just to illustrate this point. Here's some data values, and if I calculated the average value, remember that average is going to be kind of like a balance point, so that I have about the same number of points above as I do below. If I were to draw a line from each of these points to this line that I'm using for my average, these blue line segments here we would call our deviations. The deviation just means it's different, that it's the difference between the data value and our average value. This bar right here represents our average value. If I wanted to find how spread out my data values are, I could figure out what this average amount of these deviations are. The deviation is the difference between your data value and your average value. And if I want to find the average of this, what I would ideally do is add up all of these deviations and then divide by however many data values I have. But if I look at x minus x bar, as long as my data value is above average, like these points up here that are higher than the average value, these differences will be positive. And the differences down here, if I do x minus x bar because x is smaller than x bar, these differences would be negative, wouldn't they? And if I were to add up all of my differences, I would get 0, because the positive values and the negative values would cancel each other out, because that average is exactly halfway in between all those points. So that doesn't do us any good when it comes to finding an average value. So somebody smarter than me said, well, let's make these numbers positive by squaring them. They said, okay, well, let's take the square of these numbers and then they'll always be positive, and then we can divide by how many we have, and that would give us a square deviation, or an average of a square deviation. This actually happens to be, we add up all those square differences and divide by n, and that happens to be how we calculate our variance. Now, because I used an x bar here, this would be a sample, I would have to do n minus 1, and there's a reason I do n minus 1, and when we get to that in the lecture I'll explain it. But that would give us an approximation of our variance. The trouble with this is, with squaring these numbers, let's say that our units here were measured in time. If I let x be a measure of time, then when I squared those differences in times, I'd have square hours if my time was measured in hours. Square hours are a unit that doesn't make sense. That's when somebody said, okay, well then let's just take the square root of this, and then we create something that's called the standard deviation. It's a way to quantify how spread out your data values are. Guys, I'm not going to ask you to reproduce this. I just thought that this little explanation would help you understand what a standard deviation is. It's a numerical value that we can assign as a measure of spread that will help us to see if our data values are close together or if they're spread out. All right, let's now start the real part of the lecture and look at the variance. When a data set has a small amount of spread, like the San Francisco temperatures, and I forgot to read this example. Example 1 here, this data gave us the average monthly temperatures in degrees Fahrenheit for San Francisco. So for January, the average temperature was 51 degrees, February is 54, and we see these temperatures. The range in the values for temperatures from January to December for the average monthly temperature is 12. So if you live in San Francisco, you're going to be cold most of the time, but at least you'll know about what to expect for the weather. There's not a lot of a change there. Now going back to objective 2, computing the variance of a population in a sample. When a data set has a small amount of spread like the San Francisco temperatures, most of the values will be close to the mean. When a data set has a larger amount of spread, more of the data values will be far from the mean. The variance is a measure of how far those values in the data set are from the mean on average. Variance is computed slightly differently for populations and samples. The population variance is presented first, and it looks just like what I gave you up here, except that we divided by n minus 1. The reason that we divide by n minus 1 is because we're using the population data, and so the average for the population is going to be known. When we use the sample, we're going to use the x bar like I did here, and the x bar tends to underestimate the population mean as a rule, so to offset that underestimation, we divide by a little bit bigger number in the denominator. That's why we divide by n minus 1. If we let x sub I be our individual data values, and I'll go ahead and mark that. X sub I here represents your individual data values. Mu is our population mean, and n is the size of the population. So I look at the difference between my data values and the average value for the population, square those differences, add them all up, and then divide by how many data values I have. That's what we would use if we were going to calculate this by hand. But tonight I'm going to show you how to calculate the population variance and the sample variance on the TI graphing calculator, so you will need to get your calculators out. This example for population variance instructs us to compute the population variance for the San Francisco temperatures. What's the first thing that I need to do when I do this on my calculator? I put my data into a list. Once I get my data into the list, what do? These two steps are consistent for everything that we do. I've given you the steps for putting your data into a list, but just in case you've forgotten, I'll write down the keystrokes one more time. We hit Stat and then Enter. You can look at the lecture notes for section 2.2, and I have all of these steps written out in great detail, including how to clear out data in a list and what to do if you accidentally delete a list. So if you need to review that, you need to review it. Go ahead and put these data into your list if you haven't already. When I hit Stat Enter, it takes me to my list, and I don't have these data in my calculator anymore, so I'm going to go ahead and clear these out and put the data into my calculator. Once you have all the data in your list, you're going to go back to the home screen, and you do that by hitting what? Second mode, which is second quit. After we have the data in our calculator, then we're going to do the one variable stats just like we did for the mean. Do y'all remember doing that? It's Stat, Calculate, then Enter. Go over to Calculate, and then we hit Enter. So I'll do this right now, and that way we can all see what it looks like. We hit Stat, go over to Calculate, and then the first thing that's highlighted is the one variable stats, and that's what we want to calculate. You can either hit 1 at this point, or you can hit Enter, and I'm just going to hit Enter. If your screen looks like this, you'll be able to follow the steps that I'm writing down. If, however, you don't see all of this stuff on your calculator screen when you hit Stat, Calc, Enter, all you see is one variable stats on the home screen, you're going to have to put in the list manually to tell your calculator what list to use. Here I want to use list 1 for my data because that's where I put my data. We need to clear out this frequency list. We'll see what to do with that towards the end of the evening. And then you go down to Calculate and we hit Enter. When you go through this process, you will see a screen that looks like this. Notice right here, this number is our sample standard deviation. This one is our population standard deviation. Remember, S went with the sample, the lowercase sigma goes with the population standard deviation. And I told you that the variance is the square of the standard deviation. If I've got a number in my calculator for the standard deviation, all I needed to do is square that number. What you don't want to do is just write this number down, then go to your home screen and hit square, because that would be an approximate value. If you want to be precise and get the exact value, we're going to have to do a few more things. We need to grab this variable right here, and how we do that is we hit vars, locate the vars button on your calculator to find the population variance. No, we found the summary statistics for the one variable. Now we actually have to calculate the variance, because the variance is not one of the numbers that they give us as the output here. These numbers don't include the variance. They give us the samples and the population standard deviations. From the home screen, you don't even have to hit clear. Find the vars button. Press that button and it takes you to a list of variables. The variable that we want is a statistical variable, so we're going to hit 5. Looking at the list of variables that are available to us, do I want the one that's in 3 or 4? I'm finding a population variance. It's going to be 4 because this is the population standard deviation. When you hit 4 on your calculator, it puts the variable on the home screen for the standard deviation. Now all I need to do is square that, and how I square something is by hitting this square button that's right above the log. And you'll see on your home screen that 2 pops up right there. That means that you're squaring this variable. This variable has a number stored in it that we got by doing the one variable statistical analysis. And if you hit enter, that's going to give you your population variance. Here's the 4 steps you'll need to go through anytime you need to find a population variance. If you were looking for a population standard deviation, you could stop right there at step 3 because there it is. There's your population standard deviation. But because I needed to square it, I had to go through these steps then to get my calculator to put that variable on the home screen so that I could square it. When you go through these steps right here, it gives you this on your home screen, and this then would be our population variance. Make sure you put this on your calculator formula sheet. You do not want to show up to the test without having this written down, because I won't tell you during the test how to do this. Now if you've got your steps written down and your calculator's misbehaving, you can bring your calculator up to me and I'll try and make it behave. But you have to have your steps written down. How we calculate the sample variance is we use this formula. Notice we still have our individual data values, but because this is a sample variance, now we're going to use the sample mean, and then this is our sample size minus 1. When computing the sample variance, we use the sample mean to compute the deviations. For the population variance, we use the population mean for the deviations. It turns out that the deviations using the sample mean tend to be a bit smaller than the deviations using the population mean. If we were to divide by n when computing a sample variance, the value would tend to be a bit smaller than the population variance. So to offset that, we divide by n minus 1. We're not going to have to worry about how to do this by hand because I'm going to show you how to do it on the calculator. And I've already talked about why we divide by n minus 1. A company that manufactures batteries is testing a new type of battery designed for laptop computers. They measure the lifetimes in hours of 6 batteries, and the results are as follows. Find the sample variance of the lifetimes. What do I need to do first? Put it in the list. Let me clear this out, and we're going to hit Stat, Enter, and then we type in our numbers, and I'm going to use list 2 now since I've got data in list 1. Once you have your data in the list, what do? Second mode takes us to the home screen. This is going to be even easier than the population variance was. We're not going to calculate the one variable statistical analysis for this. We don't have to. We could and then go through the same steps as we did before, and instead of using the sigma x, we would use the sx for the sample. That's one way to do it, but there's an easier way, and that's what I'm going to write down here. At this point, we're going to hit second stat, scroll over to math, and then we're going to scroll down to number 8, which is our variance, and then hit enter. Or you could just hit number 8 and it would do it for you. Let me show you what I'm talking about. We hit second, stat, go over to math, and number 8 down here is variance. All of these commands underneath second stat are for sample data, not population data. That's why I had to do something different above. And this will calculate your sample standard deviation, your sample variance, all of the stuff that you want with the sample. This will put the variance command on your home screen. Now you have to tell your calculator what list you want to calculate the variance for. I put my data in list 2, so how do I put list 2 in my calculator? Second 2. You don't have to close the parentheses, it'll work if you don't. And we see that the sample variance for this data would be 2. We need to put the variance command on the home screen. Once we do that, we need to tell the calculator what list to use. We put the list into the home screen by hitting second and then the number that corresponds to the list. For this example, I have my data in list 2, so I'm going to hit second 2. I want to go through this one more time now that you have these steps written down. Start with a clear screen. I've got the data in my calculator. I go to the home screen. I'm going to start with step 3. We hit second, stat, go over to math, and then number 8 is the variance. And that pops this up on the home screen. This is what pops up on the home screen, and then you've got to indicate what list to use. So I hit second 2, and you see how it puts the list 2 in that position right there. So these commands bring up this screen, and then what you want is the variance right here. That's what your home screen looks like, and then you put this list in by using these commands right here. And that's how we find the variance for a sample. It's easier. It's probably the same number of steps, but to me it's easier because we don't have to go into the vars screen and dig through looking at variables. The screen where we find the variance actually says variance. By the way, I need to make a note. All of these commands are for sample data only. Right quick, let's go back and look at the last example that we did where we did the population variance following these steps. My data is still in my calculator, I believe, for this example problem with the temperatures in San Francisco. Watch what happens if I did this command for the variance of the temperature data. I'm just going to, oh, by the way, rather than go back into all those screens, if this is the last thing that you have on your home screen, to pull it up, notice I didn't go through the second stat math 8 thing. All I did was I hit second enter. If you hit second enter, it brings back the last command that you had on your home screen. It saves you some keystrokes if you're doing several problems in a row that you're finding the same thing. So what I need to do now is change the list number. I'm going to clear out the list 2, or I'm actually going to type over it, and I'm going to put in list 1 by hitting second 1. This is what we get for the sample variance for the temperature. Notice it's bigger than what we got for our population. That's why I said you can't use these commands for if you have population data. You have to actually do the one variable stats, grab the population parameter, and then square it. All of these commands are for the sample data only. So if you have sample data, do this. It's easy. But if you have population data, you got to go through and grab the variable after you do the one variable stats. Objective 3 is computing the standard deviation of a population and a sample. The standard deviation is just the square of the variance. It's sigma squared. Because the variance is computed using squared deviations, the units of the variance are squared units of the data. For example, in the battery life example, the units of the data are in hours and the units of the variance are in square hours. In most situations, it's better to use a measure of spread that has the same measured units as the data. Square hours don't mean anything to me. The variance is a measure of spread and it's a number that I can get, but the units don't make sense. If you take the square root of the variance, I said that wrong, didn't I? The standard deviation is the square root of the variance. Standard deviation is just sigma. Your variance units, because we squared those deviations, are going to be in units squared. So in the battery problem, our units were measured in hours. The variance gave us units of square hours, which doesn't make sense. If I take the square root of the variance, I'm square rooting those square hours, and then my units will be back to being hours. That's why we like the standard deviation. The sample standard deviation will be the square root of the sample variance. The population standard deviation is just the square root of the population variance. In this problem, we're told the population variance of temperatures in San Francisco is sigma squared equals 14.083. Find the population standard deviation. How do I find that population standard deviation? Just take the square root. Let's clear out our list so we're looking at the same thing. What I would want to do is take the square root, and I hit second square root to get to it, of 14.083. And that gives us 3.75. We'll call it 3.75. The population standard deviation is equal to the square root of 14.083, and that's approximately equal to 3.75. And we would just use our calculator to get that. The variance of the lifetime for a sample of 6 batteries was 2. Find the sample standard deviation. The sample standard deviation is going to be the square root of 2, and that's approximately 1.41. The little wiggly equal signs means approximately equal to. Here's the publisher steps for finding the standard deviation on your TI-84 calculator. They leave out some things, such as after you enter your data into the calculator, you want to go to the home screen. Then you can run your one variable statistics. When you find your one variable statistics, the SX is the sample standard deviation. The sigma X is the population standard deviation. The sample standard deviation will always be slightly bigger than the population standard deviation. Monday night we also talked about variables being resistant. Remember that we said a variable was resistant if its value is not affected very much by an extreme value. For the measure of center, which was resistant, the mean or the median? The median, the number that's in the middle, because an extremely large value or an extremely small value won't really change the middle value a whole lot, but it does change a mean. Well, guess what? The standard deviation is not resistant either. A really large value or a really small value will cause you to have a really long deviation from the mean, which means that your standard deviation is going to go up. So the standard deviation is not resistant. Objective 4 is to approximate the standard deviation using grouped data. This is very similar to what we did with the grouped data when we did the weighted average. Remember when we did the weighted average with group data? It was the last example in 3.1. We put our frequency in list 2, we put our class midpoint in list 1, and then we did the one variable stat where our data was in list 1 and the frequency list was in list 2. Let's go ahead and put this information into our calculator. I'm going to clear out my list just because you don't have to if you don't want to. You have other lists you can use. But I'm going to put the midpoints in list 1 and put the frequencies in list 2, and then we go back to the home screen. Want to make sure that you've got the right numbers in here, because if you mistype a number it will throw everything off and drive you crazy. Let's go back to our home screen now. Oops, I didn't hit second quit, I just hit mode. If you do that accidentally, just hit clear and it takes you back to your home screen. Now we need to find the one variable stat, so we hit stat, go over to calculate, and then enter. My list for my data is list 1, that's what I wanted, but now I have a weighted or a group data. I have frequencies here. My frequency list is going to be list 2, so I hit second 2 and then scroll down to calculate. We were asked to approximate the sample standard deviation. Which one of these do I want? The SX or the sigma X? The SX, because it was a sample. This is the one that I want. I don't want this one. So we would say that our sample standard deviation is approximately equal to 77.3. The last thing that we're going to go over that's going to be tested on your homework and on your exams is something called the empirical rule. This is objective 5. We use the empirical rule to summarize data that are unimodal and approximately symmetric. Another word for this is normal. A normal distribution has this general shape right here. Many histograms have a single mode near the center of the data and are approximately symmetric. Such histograms are often referred to as bell-shaped. They're more often referred to as normal. The empirical rule works only with normally distributed data. When a dataset has that bell-shaped histogram, it's often possible to use the standard deviation to provide an approximate description of the data using a rule known as the empirical rule. The empirical rule basically says that if you have your mean in the middle of your distribution and you add one standard deviation to the mean and subtract one standard deviation from the mean, you will have 68% of your data fall within these range of values. If you add and subtract 2 standard deviations of the mean, you'll have approximately 95% of your data fall between those values. And if you go out 3 standard deviations, you have approximately 99.7% of your data, which your book calls almost all, because 99.7 is almost all. In this example, we're told that the following table presents the U.S. Census Bureau projection for the percentage of the population age 65 and over for each state and the District of Columbia. Use the empirical rule to describe the data. if I give you a question like this, what I want you to do is I want you to find the mean and the standard deviation, and you do that by using the one variable statistical analyses. This is, of course, assuming that you have unimodal symmetric distribution. You look at the histogram to determine if that condition is met, that your distribution looks approximately normal. Once you've determined that your distribution looks approximately normal, we use the one variable stats to find our mean and our standard deviation. Once you know the mean and the standard deviation, we're going to find these numbers for the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard deviations, and the mean plus or minus 3 standard deviations. On your calculator, you can save yourself some time if you remember that second enter thing. For this problem, our mean was 13.249, and then we say minus 1 standard deviation, and the standard deviation was 1.6827, and we get 11.57 if we're rounding to 2 decimal places. Rather than type all that in again, all I have to do is hit second enter, move my cursor over to the minus, and change it to a plus, and then I can get my mean plus 1 standard deviation. Pretty slick, huh? If you don't want to type everything in again and do the mean minus 2 standard deviations, hit second enter twice and it'll bring back the line that was above. When the cursor is on the 1, I need to multiply this number by 2, so I'm going to hit second delete, which is actually insert, and I'm going to type 2 times that number and hit enter. And that's where that 9.88 comes from. If you hit second enter again, move your cursor over and change the minus to a plus, you get 16.61, which is the number that they got right here in the middle. That's where this number came from. Do you like the second enter? It just saves you some keystrokes and some time. The question was, if I come across a question like this on the exam or in the homework, how am I going to know how to do this? The calculations in and of themselves are not extremely difficult. Your question is, how do I know when to do these calculations? The answer is, if in the instructions they tell you to use the empirical rule. The empirical rule is the mean plus 1, and I usually write it like this, plus or minus 1 standard deviation is 68% of your data. The mean plus or minus 2 standard deviations is 95% of your data approximately, and then the mean plus or minus 3 standard deviations is going to give us almost all of our data. But the key word here is empirical rule. Does that help? Actually crunching in the numbers is not terribly difficult. These are the numbers that you would get when you do that. And then I may give you a graph on your test that looks like this, and you just put the numbers in. What number would we put in for the mean? For this particular problem, it was 13.249. If we rounded 2 decimal places, we'll call that 13.25. For the mean plus 1 standard deviation, we go over here, that's 14.93. Do y'all see where I'm getting that number? It's the mean. 13.25 is your mean. The mean plus 1 standard deviation would be 14.93. The mean plus 2 standard deviations is 16.61. The mean plus 3 standard deviations is 18.3. The mean minus 1 standard deviation is 11.57. The mean minus 2 standard deviations is 9.88. The mean minus 3 standard deviations is 8.2. Our standard deviation for this problem was 1.6827. That's approximately 1.68. If we look at the difference between these numbers, we see that it's the same. It's approximately 1.68. Does that make sense? Because how we're getting from one number to the next is we're adding that standard deviation. Now, because of rounding, we may be off just a little bit, but this is the general idea. It's always true that this difference between consecutive numbers is going to be equal to your standard deviation. Any questions about that? The question was, how do we know what percent they fall in between? If you're looking at a normal distribution, symmetric and unimodal, bell-shaped, it will always be 68, 95, almost all, within 1 standard deviation, 2 standard deviations, or 3 standard deviations of the mean. So the mean plus or minus one standard deviation means that you have 68% of your data. The mean plus or minus two standard deviations will always contain 95% of your data. And the mean plus or minus three standard deviations will always contain 99.7 or approximately all of your data. You have to have this normal distribution. This only works for the normal distribution. The empirical rule period only works for the normal distribution with these particular percents. These percents are true for these values as long as your distribution is normal. So what if your distribution is not normal? Can we find what percentage of data should fall within certain parameters? And the answer is yes, but it's not going to be this. It's going to be something different. Yeah, if your data is skewed somehow, or even unimodal or something. If our data is not normal, these percents won't be the same. This is where Chebyshev comes in. Objective 6 is to use Chebyshev's inequality to describe a data set. Chebyshev's is true for any data set. When a distribution is bell-shaped, we use the empirical rule. That's the 68, 95, 99.7. Your book calls 99.7 almost all. It's easier for me to write 99.7, so I'm going to do that. Another rule called Chebyshev's inequality holds for any data set. So if our histogram came out looking like this, where it's not symmetric and unimodal, it's just kind of all over the place, we use something called Chebyshev's inequality. In any data set, the proportion of data that is within k standard deviations of the mean is at least 1 minus 1 over k squared. At least. It could be more, but this is the minimum that it would be. Specifically, by setting k equals 2 or k equals 3, we obtain the following results. Don't worry about where this formula came from. There's a lot of mathematics that went into developing this. This is not going to be on your test, but it answers the question of where did those percents come from and what if your data is not normal. If your data is not normal, if you move within 2 standard deviations of the mean, we're going to plug in a 2 for k. If I do that, I get 1 minus 1 over 2 squared is 1 minus 1/4, and 1 minus 1/4 is 3/4. And 3/4 is about 75% of the data. So for any data set, about 75% of the data will lie within 2 standard deviations of the mean. It's very different from the 95% we got with the normal distribution. That's because you're going to have more of your data down at the endpoints, at the tails, than what we would for the normal distribution. Notice on the normal distribution, the tails are very thin. So if we get very far away from the mean, we don't have a lot of data left. Most of it's in the middle. But if your distribution looks like this, then you may have a lot more data in the tails, which is why this percentage here is lower when we're 2 standard deviations from the mean than it is for the empirical rule. If k was equal to 3, meaning we go out 3 standard deviations, then we just replace 2 with a 3 in this formula, and that gives us 1 minus 1 over 3 squared. Well, that's 1 minus 1/9, and 1 minus 1/9 is 8/9, and if you convert that to a percent, do 8 divided by 9 on your calculator, you're going to see that that's about 89%. So for Chebyshev's, we would say that if we were within 2 standard deviations of the mean, we'd have about 75% of our data, and if we were moved out to 3 standard deviations of the mean, we would have about 89% of the data. Here's an example of Chebyshev's inequality. It says that as part of a public health study, systolic blood pressure was measured for a large group of people. The mean was 120 and the standard deviation was 10. So our mean was 120, the standard deviation was 10. What does Chebyshev's inequality prove about these data? Well, if we go out 2 standard deviations of the mean, that's what this 2 right here means, then it looks like 75%, because remember with Chebyshev's, if we got 2 standard deviations, that's 75%. It looks like at least 75% of the people had a systolic blood pressure between 100 and 140. This is for the 2. If we go out 3 standard deviations, and we saw in the example above, if we go out 3 standard deviations, we're looking at about 89%. We would say that about 89% of the people had a systolic blood pressure between these two values, 90 and 150. Do you see how that works? That's it. It's just giving us a way to calculate these different percentages for distributions that are not normal. But this front part is exactly the same. It's the mean minus 2 standard deviations, the mean plus 2 standard deviations. Once you know what your mean and your standard deviations are, you just plug them into the formulas. The formula says that if you have the mean plus or minus 2 standard deviations, you're going to have approximately 75% of your data. If we do the mean plus or minus 3 standard deviations, we'll have approximately 89% of our data. So we can calculate these numbers by plugging in numbers for the mean and the standard deviation, and then we can write the conclusion between 89% of the population would have a systolic blood pressure between 90 and 150. 75% of the population would have a systolic blood pressure between 100 and 140. That's how you read that information. Does that make sense? It's not that bad, but I think if you listen to this and if you can follow this, it helps you understand the information that you have up here with the normal distribution and the empirical rule, which is on your test. We've got the same thing here. Mean plus or minus 1, 2, or 3 standard deviations is a certain percent. For the empirical, we always use these percents because our data is normally distributed. If you had a different distribution, you would use these different percents is all. This one, this is just a picture of the distribution of data that's not normal. I would not make you do the histogram on a test. It may be helpful to look at a histogram, but when you grow up and you're doing statistics in the real world, if you ever need to, you'll know at that point how to make this graph. Honestly, PowerPoint will do it for you if you can type in a list of data into Excel. That's not part of what I'm testing, that graph. So if that's what's freaking you out, you're good. Objective 7 is a coefficient of variation. This is not difficult. It's not going to be on your test, but I want to explain it because it is a way that we can compare the measure of spread for things that are measured on different scales. The coefficient of variation, or CV for short, tells how large the standard deviation is relative to the mean. It can be used to compare the spreads of data sets whose values have different units. So the coefficient of variation is just this formula. You take the standard deviation divided by the mean. That's called your coefficient of variation. In this example, we're told the National Weather Service records show that over a 30-year period, the annual precipitation in Atlanta, Georgia had a mean of 49.8 inches with a standard deviation of 7.6 inches. This value right here is the mean rainfall. This value right here is the standard deviation of the rainfall over 30 years. The annual temperature had a mean of 62.2 degrees and a standard deviation of 1.3 degrees. Compute the coefficient of variation for precipitation, that's just rainfall, and temperature. The coefficient of variation for the rainfall is found by taking the standard deviation for the rainfall, which was this value right here. My stylus died, so I've got to use my mouse. I'm sorry. That's where the 7.6 came from. That's the standard deviation for the precipitation. And then we divide it by the mean for the rain, the mean for the precipitation, and that was 49.8, this value right here. When we look at the ratio of those two numbers, we get 0.15. If we do the same thing for temperature, we take the standard deviation for the temperature right here, we divide it by the mean for the temperature, the 62.2, and when we look at that ratio, we get 0.02. Because the coefficient of variation for precipitation is larger than the coefficient of variation for temperature, we say that the precipitation has a greater spread relative to its mean. It gives us a way to compare things that are not necessarily similar measures. This wraps up section 3.2. This is one lesson that you may need to go back and watch the video again and look at the lecture notes, because some of these concepts are straightforward. Some of them are a little slippery, and it may take multiple exposures in order to fully grasp and understand and get comfortable with it. When you're watching these videos, don't feel compelled to hit play and watch from start to finish. If I give you the lecture notes so that you can fast forward and watch your computer screen, and when it gets to about the place in the lecture notes that you want to watch, just watch that piece that you're interested in. There's no need to sit and listen to me talk about range for 5 minutes if really what you're interested in is the empirical rule. This wraps up section 3.2.